Hello, here's the final section of the 2007 PAT. This is the maths section, so 1 hour it says here for this. No calculators in this part of the test. You can use it in the physics part, but not in this bit. So that shouldn't hold us back though. So let's have a look at these. We've got standard difference of two squares to begin. So evaluate that. This is one of the reasons you can't have calculators. So we're going to have 6667 minus 3333 multiplied by 6667 plus 3333. So that is what we got there, 3334 multiplied by 10,000. So 3334 and then 4 zeros at the end. So nice easy starter for 2 marks. Find the equation of the line which is tangent to the curve y equals x to the 4 at the point minus 216. So our gradient then is good. Well, y dash is 4x to the 3, differentiating it. So our gradient, we want x is minus 2 on this. So we've got minus 8 times 4, so minus 32. And then we just need to do equation of a line. So we've got y minus 16 equals minus 32 x plus 2. So far so good. Evaluate this thing, these logs. So 2 log 125, so 125 is 5 cubed, so that's 6 log 5, and we got 6 log 5 at the bottom as well, so we got 1. Actually writing those out, you just got to change them into the powers. 125 is log 5 cubed, take the 3 down to the front. So question 4, 2 dice are thrown. What's the probability that their numbers add up to 6? So for 6, we'd have 5, 1, 4, 2, 3, 3. I should have done these with pluses rather than 2, 4, and then what we got, 1, 5. So that's 5 out of 36. So we got 5 out of 36 for part 1. And then they add up to 11. Well, we're just going to have 2 permutations for that, 5, 6 and a 6, 5. So that would be 1 out of 18. Right, expand 2 plus x to the power of 5 in ascending powers of x as far as the term x cubed. Right, so we're going up. So if it's the 5th level of Pascal's triangle, then that is the 1, 5, 10, 10, 5, 1 layer. So we just need up to x cubed. So that will be these ones. So we're going to have, what we got then? 2 to the 5. When am I going to write this? Let's squeeze it underneath. We've got 2 to the 5. Then we're going to have 5 times 2 to the 4 x plus 10 times 2 cubed x squared plus 10 times 2 squared x cubed. So that has given us all in all 32 plus 80 x plus 80 x squared plus 40 x cubed. Nice. In the figure shown below, the triangle is equilateral. Find the ratio of the areas of the larger to the smaller circle and the larger to the smaller shaded region. Right, this one, I suppose it depends. I mean, you can quote this. We know if you've got a circle inside a triangle, then the height is divided into 3. So if we've got an r there, we've got a 2r here. You can show that quite easily by splitting it into 6. If you split the this circle in the triangle into 6 bits, so each one of these has got 60 degrees here, you've got a radius of r, so we can work out that must be 2r because 2r cos 60 is r. So we can see that dropping out from that construction. We've been through that loads of times in geometry videos. So it makes it easier now for larger to the smaller circle because the that's just then going to be 4 to 1 because it's doubled the radius. So that is going to be 4 to 1. Now the larger to the smaller shaded region. So the larger, well, we can multiply that up 3 times, because if we do all of that and that as one shaded region and that, so we've tripled each one of them, it's going to keep the ratio the same. So we need to do the ratio of big circle minus triangle to triangle minus little circle. That's what we're looking to do there. So the triangle is going to be, so the base, half the base is 2r sine 60, so that's root 3 times r, and then multiplied by the height. So we've got 3 root 3r squared, 3 root 3r squared. That's for our triangle, 3 root 3r squared. And we've got the big circle was 4 pi r squared, and the small circle is pi r squared. So we've got all of that. We can divide by our r squareds. I mean, I'm not really sure how much more they're going to want on this. I mean, that is a ratio of areas. Whether they, I mean, you could say they might want to divide one of them through, but really this is all we've got. It's that to that is our ratio of that one. Sometimes you see people presenting ratios as fractions. I mean, often I do that myself, where you'll just divide one out. You'll say, okay, we've got that divided by that. Yeah, it's more or less just setting one side equal to 1, and then you leave that bit out and just write it as a fraction. So yeah, that's all good. But yeah, that finding with the circle inside the triangle is certainly one which is worth remembering and knowing where it comes from as well, because it's a quotable finding that you can use in these. It comes up quite a lot in geometry questions. Question 7, sketch the curves y equals x squared, y equals x minus 2 squared, and y equals, well, the two of them combined on the same graph. So on the same graph, that'd be interesting to do. They're all squared, so we're not going to have anything negative on this. I'm going to have a bit more on the right hand side because clearly that's been shifted to the right. So let's draw the y equals x squared, which is going to be, oh, it's not bad for me on here. So we've done that one. So that is y equals x squared. Then this is a shift 2 in the x direction. So if we move that to 2 and then try and draw it parallel to the original one, okay, it's gone a little bit wonky, and that will be going through 4 over here, because when x is 0 we're going to get 4. So that is y equals x minus 2 squared. And now this last one, so let's have a swap of color. We're just adding the two of them together. So so this has gone through 1, 1 here. So it's going to go through, this is where my scale is going to be a little bit out. The bottom there, that coordinate is going to be, so this point here, that's got to be at 1, 2. We've added them together, so we're going to get 1 from there and 1 from there. And then we're just adding the 2. So it's got a touch here, because that's where we got 0, and it's got a touch here, yeah, which is where we've got 0 here. It's getting a little bit wonky again. But everything is going to be above this line, because now this line that we've got here from the x minus 2 squared, we're just adding stuff onto it. So it has to stay above it, and it has to hit a minimum here, and then touch there, and then stay above it again. So we're getting that. You need to make sure that this final one is not crossing below the other ones. It can't go below either of them. It's touching this one at this point, and it's touching this one at this point, and then staying above it all the way through, because we're just adding up positive numbers. So yeah, as sketching ones go, that one is nice for 5 marks. I've seen, yeah, some horrible ones compared to that. Right, question 8. Solve the equation tan theta equals 2 sine theta from 0 to 2 pi inclusive. So, right, let's do a little sketch then on this one. So our tan theta will be doing that up to 2 pi. Let's go back to blue. Our sine will be coming through here and here and here. So we're going to have, oh dear, after drawing in that bit, I've then missed it by a mile. So it'll be going through there. So we can see then, because we're including 0 and 2 pi, so we know we've got 5 solutions then. So we're going to have 0, pi, and 2 pi. And then we're going to have the ones where, if that's sine theta over cos theta, it's going to be where cos theta is a half. Because we're changing that into saying we've got sine theta over cos theta equals 2 sine theta. Now, we haven't jumped straight to that, because if you divide just through by the sine thetas, then you're losing these solutions, because you're losing the sine theta equals 0 solutions. Then we flip these around, we've got cos theta equals a half. So we're going to end up having, what's that, pi by 3, and then 2 pi minus pi by 3. So we've got pi divided by 3 and 5 pi divided by 3. So 5 solutions all in all. Right, question 9. Show that the points minus 5, 4, well, all these 3 points lie at the 3 corners of a square. Find the coordinates of the 4th corner and the area of the square. Right, a little sketch on this. I shouldn't have used up so much space on this this thing. But yeah, let's do a little idea. So minus 5, 4. So if we had a tentative XY plane there, and then minus 5, 4. So let's leave some space. So somewhere over here, say, that's our minus 5, 4. Minus 1, minus 2. So somewhere here-ish. Minus 1, minus 2. And then 5, 2. So somewhere, say, there. It's a bit rough. Change colour again. So the nice thing with squares is you can just fill in the bits on the outside with triangles. So if we were going to have, we need to show there's another point up there, and we need to have all of these bits turning into the same triangle. So what have we got here for changing x? We've got a 6 there and a 4 there for y. So, and then have we gone 4 back in x? Yes, we have, from minus 1 to minus 5, and we've gone 6 up. So this will then be 4 up and 6 across. So that's going to be at 1, 8, I think we've got. Yeah, and I'm just seeing that it adds up with this one as well, because that would be 6 up, which would make 8, and then 4 back, which would make 1. Right, so we've definitely got the coordinate at 1, 8. And then we want the area of the square. So the area of the square is going to be 100 for the red square, minus, we've got 4 of these rectangles. So we've got minus 4 lots of these triangles, so 2 lots of these rectangles. So that's 6 times 4 times 2, 2 times 24. So we've got in then 52. If they haven't given us any units, so the area is 52. Other methods apply. You could do a vector thing on this. If you get 2 vectors and then showing that they're perpendicular to each other and of the same length. The geometrical approach, a sort of Cartesian coordinate approach, to me is just way quicker when you're approaching those sort of things. Oh, blimey, we've still got 3 to go here. Evaluate, maybe even more. But yeah, we've got to evaluate this integral. Right, wonderful. So we've got then, well, we can just jump straight in, really. We got x to the half, so that would be 2/3 x to the 3 over 2 when we integrate it. X to the minus a half, so that would go to plus a half, so 2x to the half. And then that's from 1 to 9. Right, so that gives us 2/3, if I can write properly, 2/3. So x, so 9, square root it 3, cube it to 27. And then we've got 2 times 3 is 6. Then we have to take off that for ones. Oh, well, take off 2/3 and take off 2. So what is that all in all? 18 plus 6 is 24, minus 2 is 22, minus 2/3 gives us 21 1/3. So that was a nice one for 4 marks. Question 11. The first two terms of a geometric progression, first term A, common ratio R, is the same as the first two terms of an arithmetic progression. Okay, so they're telling us that we've got A, R is A plus D. So yeah, that's the first term of each one. In the geometric, we've multiplied by R. In the arithmetic, we've added D. And then the same for the next one. So we multiply by R again, or we, what did it say? The same, the third term is twice as big as the third term of the arithmetic progression. So 2 lots of A plus 2D. Right, so that's fine. Find different expressions for D and hence or otherwise find 2 possible values of R. So, right, well, we're saying then that, what are we doing? Find 2 different expressions for D. Well, we just rearrange these 2 things for D. So D equals A R minus 1. And then we've got that D is going to be equal to, well, we're going to have a half on the outside. We'll have a half AR squared minus A. Okay, we probably do want to tidy that up a little bit because that does look like a mess, really, doesn't it? So, yeah, let's tidy it up then. So we're going to have a quarter of A, well, take the A out as well, R squared minus 2. Okay, yep, so that's 2 expressions for D. We can set those equal to each other and then we're going to get an expression for R, which is what we want, I think, isn't it? Yeah, so that's what they're asking for. So I'll multiply by 4 while I'm at it. So 4A R minus 1 is equal to A R squared minus 2. Cancel the A's, so we've got R squared minus 4R minus 2 plus 4, so plus 2 equals 0. That is then going to be R minus 2. I'm going to complete the square because it's so nice to do. Minus 4 plus 2 equals 0. So R equals 2 plus or minus the square root of 2. Right, that was pretty good. Is question 12 going to be the last one? Yes, it is. Right, question 12. Isosceles triangle has sides of length x, x, and p minus 2x, where p is the length of the perimeter. Well, it would be. Find the value of x which maximizes the area of the triangle for fixed p. So that changes our approach a little bit, and all the angles of the triangle for this value. Right, so we want to maximize the area on all of this. So the area of the triangle, so they're saying we've got something that looks a bit like that, p minus 2x, although that p minus 2x might be longer than x. I mean, there's always that possibility, but that doesn't really matter in our picture. So that is going to be a half of p minus 2x multiplied by the height, half base times height. But we're also saying that, so you can use Pythagoras to say that x squared is going to be equal to h squared plus p minus 2x over 2 all squared. That's just our Pythagoras splitting that isosceles in half. So this looks really like a big mess, all in all. We can sub that h in. A half, we are getting 6 marks, and I suppose it's not particularly complicated algebra to do this, I suppose. X squared minus p minus 2x over 2 all squared, and that's to the half. So yeah, let's square out the thing that's on the inside, I suppose. Move across the page because I think this is going to take up a lot of space. So we've got that. I think we can go to small bracket x squared minus what we're going to have, p squared over 4. Then we're going to have plus, so that's going to be, what we got? We got minus 2 minus 4px. So we're going to end up squaring that. It's just going to come out at minus, well, let's do the 2x squared bit. So we got, yeah, that again is going to cancel. That's just going to be x squared. Oh, we got a minus there. I'm getting my minuses mixed up. So that is going to be a minus x squared. Let's come back to this one again. So we've got a p times, I don't know, my mind's gone blank. I think I've been staring at this too long. So we got p times minus 2. So we got minus 4px divided by 4 gives minus px, and then the minus gives us a plus px. Right, I got there in the end. It's the trouble when you get to question 12, you start freezing up on these things. So that's a half of p minus 2x. We need to deal with this fraction in here. I don't like having fractions sitting around like that. Oh, the x squareds have gone away. That is nice. They've cancelled. So let's take that out and make it a quarter. And we'll have a 4, yeah, so 4px minus p squared all to the half. I think that's what we've got in there now. Yeah, just getting that quarter outside because we can square root it. These have cancelled, so we'll have to have a 4 in front of the px. Yep, so that's looking good. So that's our A. We want to maximize that. P is fixed, so it's x that's changing. So we want to do a dA dx, which means we're going to have to do product rule on this. So yeah, so we're going to product rule this. So we'll leave, so we've got a quarter, leave the first one, and then differentiate the second one with respect to x. So we're going to have another half, we're going to have a 4p, and then we're going to have 4px minus p squared to the minus a half. And then we need to add on, so we leave the quarter, leave the other one, 4px minus p squared to the half, and then differentiate that one, which is going to give us a minus 2 on that. So multiplied by minus 2. Right, so that's our dA dx. We've got some things we need to try and figure out in all of this. So that's going to cancel with that. And we've now got p over 2, p minus 2x. This seems overly complicated. Maybe someone's going to have a quicker way of doing this because this doesn't seem very good at all. That's going to be minus a half times 4px minus p squared to a half. Right, so that's our dA dx. We have to set that equal to 0. It might not be that bad, I suppose. We're going to get some various things cancelled. So when these things are equal to each other is what we're after. So we've got, we can get rid of those halves. So we're going to say that p times p minus 2x. Let's multiply through by this because we've got it to minus a half there and plus a half there. So that will be equal to 4px minus p squared. Yeah, okay. Now the p squared, oh, we can cancel a whole load of p's. And then we've got p minus 2x equals 4x minus p. So 2p equals 6x. So x is p over 3. X equals p over 3, i.e., oh, that's a relief, equilateral triangle, as in, yeah, each length is the equilateral, yeah, because, yeah, if we've got p over 3, and then we've got p minus 2/3 of p, so p over 3. Excellent. So, and all the angles of the triangle. Well, they're all 60 degrees. Okay, so that last bit was fine then. I wonder if there's got to be a better way of doing it than that, some kind of geometrical approach. The thing that worries me about jumping into some other method is this fixed P thing, because you get stuff with, say we had a triangle where the P wasn't limited. You can, it's like moving it towards, I don't know. I don't know whether that's going to affect things with this fixed P, whether you can do, I'm trying to think, if you start off with a really skinny triangle and lower the top down and see how the area is changing. I suppose it is that then midway down. There's got to be some symmetry argument for why that is a maximum, in the same way as you do with a square. If you start with a really tall, an elongated rectangle, and you keep changing it, eventually you hit this symmetry point where you then go out the other side. So it keeps on increasing, and then it must be decreasing again once you've gone through the symmetry point, because you could start at either end through symmetry. The bit in the middle must be where the peak is. So I'd imagine you could do the same thing with this. If you're comparing that and that, as in being more or less the same thing, that we're squashing this triangle down, and you've got some position in the middle. But I suppose it's just harder. You can directly, with the square one, you can directly say that these 2 points, whether it's standing a rectangle upright or on its side, are identical. Whereas you can't quite say that with that position and that position. So you can say, oh yeah, the area is increasing as you move towards this, and the area is increasing as you move towards this from each end, but you don't have the same immediate symmetry argument for saying that the equilateral triangle must be the maximum in the middle. But I'd imagine there's going to be some variation on that you could do if we could be bothered to play around with it. So yeah, maybe I'll have a look at that closer. This is certainly a safe approach, I think, if you're tackling it in an exam, because providing you know how to do the product rule, all you're doing here is some GCSE geometry and then a bit of algebra, and then you do your calculus at the end. And yeah, you're usually pretty slick at doing calculus if you're applying for Oxford. So yeah, that's the safe exam approach. But I think from a more satisfactory, more elegant approach, there's got to be some kind of symmetry thing that we can do with these changes in triangles, looking at it geometrically. Anyway, that's wrapped up the whole of the 2007 PAT. So it's split across 4 parts. So hopefully that's been useful.